Okay, today we start our review. So we are done with new stuff. There won't be any more homework. It'll be a fairly short review assignment because it's only on one chapter or something. But no regular, that's just an extra credit assignment. So what's going to be on this test? First, it's cumulative over this semester. So while, of course, forces were used this semester, even though they weren't introduced this semester, there could be force problems, but you're not going to have, a simple, so we have 3 forces acting on this tree, what's the net force? Right? It would be, where forces come up would be something like, you have a charged particle with a charge of, +2, and over here you have this and this, what's the net force on it? You're using net force ideas, but it was going to Coulomb's law, and that's what the purpose of the problem was, but it still required you to have that knowledge for first semester. So, all of the problems have for their purpose something the second semester, but there always is carryover because physics builds on itself. Now, you're probably not going to have anything that has to do with sound, right? Because there's not much carryover from sound in what we've done this semester. So, the layout of the test will be just like the other tests. The questions should be a little shorter for you to do because when you're taking over such a broad range of topics, you can't expect people to have as in-depth knowledge of what they studied 3 months ago. So it's the same number of problems, but they should be a little bit shorter to do, hence 2 hours instead of 3 hours. It should be doable in that time frame. So you do have 2 hours. I don't remember when the test period is. I'll tell you on Friday. Yeah, Tuesday. Okay. Yeah, I think it's 1 on Tuesday. I think that's correct. 1 to 3. And as with first semester, I hope to get the last exam graded today, and then I will upload the scores and send out a spreadsheet where you can see, what would happen to your grade if you get different grades on the final exam. And you can drop the final exam just like you can drop any other exam. Okay, let's get into some review stuff. So we start with electricity. Know that there are 2 types of electric charges. And so those were, Ben Franklin just randomly chose whatever is on the amber is going to be negative. And it was electrons, so electrons have a negative charge. And then the positive charge carrier is the proton. And charge always comes in quantized amounts, integer multiples of the charge of an electron. Now, people in Physics 252, yesterday, we talked about quarks. And quarks having charges of plus 2/3 electron charge or minus 1/3 electron charge. But since you never get a quark all alone, they always combine either a quark-antiquark pair or 3 quarks, or there is an option of 3 quarks and 2 antiquarks, I think it is. I don't know, there's an option with 5 that has at least some people claim they found. But you always end up with the integer number of electron charges. So we stick with that. Found by itself, you always have an integer number of electron charges. Simple rules, likes repel. So negative repels negative, positive repels positive. Opposites attract. What about neutral? Let's say I have something with a charge of 0 and something with a positive charge. Okay, to first observation, no force. No net force because 0 charge means that it doesn't interact via the electromagnetic force. But of course, that 0 charge object is probably not made out of neutrons. If it was made out of neutrons, the no force would be the perfect answer every time. But if it's made out of real atoms, if it's like, let's say, a piece of metal, metal has electrons that can move about. And if I bring a positive charge close to a piece of metal, what's going to happen to that metal?
It's going to attract the electrons.
It's going to attract the electrons. Perfect. And so the electrons come over, and the electrons are closer to my positive object than the rest of the charge. So you would have then a dipole, a situation where you would have induced a dipole. You would have, here's my positive thing, here's my thing that was originally neutral, but electrons have been pulled over here, leaving this side positive. And then we have Coulomb's law. Force is equal to K Q1 Q2 over R squared. And this is like tides work on Earth. We have the stuff that's closer, 1 over R squared is a smaller r, so it's a bigger force. And so the attractive force between the positive charge and those negatives is stronger than the repulsive force between the positive charge and the positives that were pushed away. And so now you have an actually net attraction. This doesn't come anywhere close to the strength that we would have had if this had been a negative charge instead of a neutral charge. But that's an induced dipole ion. I just talked in my physical science about chemical bonds. And you have covalent bonds and ionic bonds. And then the next, going way down in strength, something that's an intermolecular bond rather than atomic bond, is ionic induced dipole. And then after that, of course, you have dipole, dipole, so on. Right? You guys have all taken chemistry at some level. Probably know that more than you know physics. So, basic rules. Coulomb's law is the equation I just wrote. Electric field. We use electric field as a way to make it easier to do our electric charge or force problems. So the point of the electric field is to make it easier. The electric field is defined the same way as the gravitational field. The electric field is the electric force divided by charge. So if I have a point charge, I'll have those two Q's cancel, and it's K Q over R squared. So that's the electric field due to a point charge. Now, if it's not a point charge, you're just going to add up the electric fields from all of the charges. And where this makes life easier is if you have a uniform charge distribution. Like if I have charge spread out over this entire tabletop, and I want to find the force on a particle right here, well, it's a huge amount of work to calculate the force between each part of the charge on this tabletop and that point, and add them all up. But if we can find the electric field that's just caused by this tabletop, which we use Gaussians Law to find, then it's easy to find the force. So that's where it becomes easier. When we have a charge distribution that has some symmetry or some way of us calculating the electric field easier. Because of this relationship, the electric field direction is always pointing the direction that you would have the force on a positive charge. So since light's repelled, if I have a positive charge here, out here a positive charge would be repelled and going away. Hence the electric field is going away. If I have a negative charge for my fist and a positive charge out here, that should be attractive because opposites attract, so the electric field would be going inward. So electric fields always point away from positive charge into negative charge. And if I know the electric field, I just take this equation and reverse it. Let's see, I think this will work. To find the force is equal to charge times electric field. So that's what electric fields are about. They're very useful to us. Electric field lines, they start and end at charges or infinity. So they can't just start or end some random place at charges or infinity. Contrast that to magnetic field lines. What do we have about magnetic field lines? They never end. They form loops. The difference in those is because magnetism, with magnets you have two poles again, two types of charges, the north and the south, but you can never get the north and south separated. They always come together for a net magnetic charge of 0. And because you always have a net magnetic charge of 0, you never have a starting or ending point. They always loop. We'll get to magnetism in just a moment here. The electric potential is not shown here. It must be on the next slide. So we'll just end with what's here and go to the next slide and talk about there. Gauss's law. Gauss's law is useful if you have a nice symmetry. If you have a spherical symmetry or if you have a cylindrical symmetry, or if you have a planar symmetry. The people in physics 252 have done problems with all of those. The people in physics 152, I think only spherical symmetry. Gauss's law says because the electric field strength is proportional to the charge, if I make a closed surface, the strength of electric field coming out of that surface is proportional to how much charge is enclosed. And so we talk about the strength of the electric field coming out is the electric flux. It's the electric field dotted to the area. What does dotted mean? Yeah, multiplying the parallel parts. And of course, then you have, if I have the tabletop here, what direction is the area of this tabletop? We define it as the normal direction. So the direction of the tabletop is coming directly up out of it. So when you're calculating the flux, you're calculating how much electric field is going straight out of your surface. And so if you have a sphere, then the surface has an area of 4 pi r squared. And if you have a spherical symmetry, that is the charge is spherically symmetric inside of that sphere, then you're going to have the same electric field everywhere pointing either in or out, and the flux becomes very easy. Got to change colors now that I'm on a white background. That's changing colors. There we go. That's the symbol for flux. So for a spherical distribution, the flux is the electric field times 4 pi r squared. Sure you're on my list, Jordan. Okay. The rest of Gauss's law is that the flux is equal to the charge enclosed divided by epsilon 0, where epsilon 0 was correctly identified yesterday as the permittivity of free space. It's always easy to get confused about those little Greek letters. The permittivity of free space is basically the breakdown voltage to cause arcing in air. And so using this relationship, if we have spherical symmetry, that's going to be electric field times 4 pi r squared. And so solve that for electric field. And that's the equation that gets you the electric field for a spherical distribution of charge by Gauss's law. Does that look the same as the equation for electric field up above? It actually does, with the definition that K is defined as 1 over 4 pi epsilon 0. You are correct. I can see it just fine. Difference in screens. Is this better or worse?
Way better.
That's the definition of K. K is a derived constant based on epsilon 0 and pi, which are considered fundamental constants. And so with that definition, K, Q over R squared is the same as Q over 4 pi epsilon R squared. So they are the same equation. Two different ways of deriving it. People in physics 252, you could have problems with different symmetries. People in 152, that's the only symmetry you have to worry about with Gauss's law. And the most important thing for you to know is generally going to be the meaning of Gauss's law, but you could have a problem that requires calculation as well. Conductors and insulators have a very basic differentiation. Conductors, both of electricity and of heat, have electrons that can move about. Whereas insulators, they have electrons, but they can't move about. Metals the whole way a metallic bond works is you delocalize the electric charges. You have a couple valence electrons that instead of being bound to the nucleus are simply bound to the metal as a whole. And in that case, then you can freely put an electron over here and take one off over here. It doesn't care, right? Electrons will just move, migrate. And so conductors, the electrons can relatively freely move. A superconductor, the electrons can move really, really freely. There is a certain amount of energy required to move an electronic conductor. The amount of energy required to move an electron in a superconductor compared to in a conductor is about a factor of 1 billion times less. So superconductors, you think about a piece of copper wire. It takes very, very little energy to make current flow through it, right? It has a very low resistance. If you divide that by 1 billion, that's what it's like for a superconductor. And you can think about just how beneficial this would be for humanity if we had superconductors available to us readily. Because then we could take things like the wires that distribute energy to our homes, and we could make those wires so they don't eat up any energy at all as we transfer the energy from one place to another. That would be a real good benefit for us. And of course, you want to make something like an electromagnet. We'll get to this in a few moments, but you wrap a wire in a coil and it makes a strong magnetic field. If you had that electromagnet made out of superconductors, that is, wires were superconductors, it costs you no energy to make that magnet because you have the charge moving, but no energy being removed from the charge as it's moving. And so you can save a lot of energy. Or many of us use computers. And when I say many, I mean everyone, because you have to submit things like homework on computers. Those computers, the big impediment to speed is the heat that's generated because of resistance in your connections in the computers. You can make them out of superconductors. You can make a lot faster computers that require much less energy. Hence, you could use the battery for a much longer time. Although I got to say the displays are the big hog of energy these days in your portable devices. So that's the difference in conductors and insulators. Voltage, electric potential, voltage. Same thing. So electric potential is defined as change in electric potential is equal to change in potential energy divided by charge. Kind of reminiscent of how an electric field works, except for this is a scalar instead of a vector like electric field. And in fact, if you go to higher levels, we will combine electric field and voltage together in a 4-vector for you with a scalar and a vector there. This was used on both of the last two tests, this very equation. You had a situation where a charge goes through a voltage difference. So let's say it's an electron. And it goes through a voltage difference. The last homework problem or test problem, it was 100 volts. Now, if the electron is going to be moving to the right, is the electron attracted to higher voltage or lower voltage? Higher voltage. Why is it attracted to higher voltage? Okay, there are two fine answers. One is that opposites attract, and higher voltage is associated with more positive charge. Another one is they naturally go to lower potential energy states. And since change in potential energy was related to voltage in delta Q, that one you said you can't see. So if it's going to naturally move, it needs Q delta V to be negative. And since Q is negative for an electron, delta V is going to have to be positive. So it's going to have to go to the positive side. So I'm just going to say that's 0 and that's positive 100 volts. There's a 100 volt difference. Now as it goes through here, is it gaining or losing total energy? Trick question. There's no friction acting on it. So it's not doing either. The total energy stays the same. And so the total energy is kinetic energy plus potential energy. Change in energy is 0 is change in kinetic energy plus change in potential energy. So that means the change in kinetic energy has to be minus the change in potential energy. And so in that problem on the test, we can go from an electron goes through a 100-volt difference to say, well, it's got to be going to a higher voltage because it started at rest. And then we can calculate its kinetic energy because it's minus the change in potential energy, which means it's going to be minus Q delta V. And so kinetic energy final minus kinetic energy initial, which started at rest, is equal to minus Q delta V equals minus E, that's the charge of an electron, right? Times 100 volts is minus 100, I forgot the minus sign out here, is plus 100 electron volts. So the final kinetic energy, 100 electron volts. Why do we use the unit of electron volt? So I didn't have to pull out a calculator. Of course, charge of electron is 1.602 times 10 minus 19. I can multiply that by 100 in my head. But generally, it's not so easy. Now, to finish out that problem, you were supposed to find the de Broglie wavelength. Because it says, what's the wavelength of, was it an electron or was it a proton? Okay, electron, good. So I'm true to the problem. So if you're going to find the de Broglie wavelength, de Broglie said it should be Planck's constant over momentum. So I needed to finally go from kinetic energy to momentum. Well, what is kinetic energy? Kinetic energy is 1/2 mv squared. Another first semester idea that's still relevant second semester. Since momentum is mv, then v is equal to momentum over m. And so this is 1/2 m times momentum over m squared. Or more simply, kinetic energy is momentum squared over 2m. And so all I had to do at this point was solve momentum is square root of 2m kinetic energy and put that in there. So I finished out one of the problems that was on the test just to make sure you understood it. Most of it, the stuff that is in, well, actually, the stuff in purple plus on the right side in green was stuff from chapters 18 and 19, mostly 19, as well as going back to chapter, 5-ish? And then this here was the new thing that the problem's purpose was. But it had the other to make sure that you have maintained currency in the topic. Okay, all charge goes to lower potential energy. So the electron went to higher voltage because that meant lower potential energy. A proton, to go to lower potential energy, what kind of voltage is it going to go to? A lower voltage. So they go opposite directions in terms of voltage, but it's because they're going toward lower potential energy. Then we had the capacitor, or as one of my buddies like to call it, the capacitator. The capacitor is a device that stores energy in the form of either a charge separation or an electric field, depending on which way you feel like talking about it. So the capacitor is defined with these relationships. That is, capacitance is defined as the charge separation divided by the voltage difference. So capacitor, two parallel plates of equal length, and the charge separation, you're going to have plus Q on one side and minus Q on the other. If you start with two plates that are neutral and you connect it to a battery, you're going to have charge leave one and arrive at the other. What kind of charge moves through a wire? Electrons. So if I take my capacitor and I connect it to a battery, how do you draw a battery? Okay, I drew a single cell because of space. Single cell, many people draw a battery that way. I have a long line and a short line. You see the difference between the cell and the capacitor is the the lengths are not equal. Which side is positive on my cell? The long one is the positive. That's why you do them different lengths, so you can identify which one's the positive side. And so what happened when I connected this up was that the positive attracted electrons. So I had electrons that flowed away, leaving a positive charge. But the cell or battery doesn't store charge. All it does is give it energy. And so those electrons got kicked through and put on the other side. So you have the amount of electrons that left the positive side, the amount of electrons that arrived at the negative side, hence the same charges on both sides. Also, we have energy that is stored as you move the charge. The first electron over goes free, right? Because there's nothing repelling it. But as soon as one electron's passed, the next one has to go through a voltage difference. And so as the charge moves, it's more and more energy. So the total energy required to move the electrons is 1/2 the capacitance multiplied by the voltage difference squared. So that's how much energy was stored, because that's how much energy it took to build the energy stored. And then you can connect it to something and discharge it. So we have things like a camera flash. A camera flash has a single cell. So that's like 1.4 volts, let's say. That's a very high voltage for a single cell. Has a resistor, a capacitor, a switch that can go between there and here where you have the lamp. So there's a charging resistor, the capacitor, and the lamp. That charging resistor is fairly large. It's fairly large so that it takes a while to charge up the capacitor. But then when you flip the switch, you have a very low resistance in the lamp, and it discharges really, really quickly. And so last thing here, and actually it's probably in the next page. No, it's not. It's going to be somewhere, is the relationship that for charging or discharging a capacitor, your current, this here is the equation for discharging the capacitor, but it's an exponential decay. For charging, it's going to be an exponential rise. This is for charging. So you have the time factor. What do we call RC usually? Instead of writing RC, we put the Greek letter tau, and we call it the RC time constant. One of those really original names to make it easier to write. And when we get to inductors, of course, we have a similar thing, but the time constant is not RC anymore. Okay, next we have electric circuits. Most important thing about electric circuit in my mind is the circuit part. If you don't have your circuit complete, then you don't have anything exciting happen. So you have to have a complete circuit. We define current as the rate of charge flow. So I is equal to delta Q over delta T. Units of Q, of course, coulombs, time, seconds. So current is in coulombs per second, which is the unit ampere. And then we have a really funky thing that the ampere is the defined base unit. And the coulomb is derived from the ampere. So in truth, instead of saying an ampere is a coulomb per second, we should say that a coulomb is an ampere times a second. So current is the rate at which charge is flowing. If I don't have a complete circuit, that current's going to be zero. Georg Ohm noticed that in most materials, there's a relationship between the voltage difference and the current going through. So we have the voltage difference from one side of a resistor to the other is the rate the charge is going through, the current, multiplied by this resistance. Resistance in units of ohms. So things with higher resistance means that it's going to require more energy, that has a bigger change in voltage, to get the charge through. Power is the energy per unit time. So since voltage is the energy per charge and current is the charge per time, then power is just voltage times current. I said it the opposite direction I wrote it, but they're both correct. Power is current times voltage, voltage times current. So the power that is dissipated is power removed from a circuit. Resistors always dissipate. Power added to a circuit by something like a battery. If I have a resistor, if it's dissipating energy and the current's going as shown, you always are going to have a voltage drop. And so you always have your plus and minus signs on a resistor relating to the current arrow as shown in that picture. And that's really important when you're doing a circuit problem. You have to identify which direction the current is going, and then based on that, which side we have positive and negative voltages. So Ohm's law was one of our important rules for solving any circuit equation. Then we had Kirchhoffs laws, which I'm sure is on the next slide. Kirchhoffs laws. We have the loop law and the node law. The loop law is a statement of conservation of energy. It says if you go around a loop and come back to where you start, you're going to be at the same energy state. So the sum of the voltage changes on a loop is equal to 0. The node law, I'm going to change, see if I think this comes out better, is a statement of conservation of charge. The sum of the currents at a node is equal to 0. That is, charge coming into a location is equal to charge leaving. Can't create or destroy charge or store it in a circuit. Now, if I say you can't store it in a circuit, you might say to me, what does a capacitor do? And what's my answer? It stores a charge separation. The net charge of the capacitor is still 0. Yes, it is easier to see the blue than the red. Can y'all read the red? Okay, just want to make sure people aren't, oh, I don't know, you wrote something. Hazards and uses. Approximately what currents can you feel? Somewhere around a milliamp you can feel. Approximately what current is going to cause me to have an involuntary muscular contraction? About 10 milliamps. Approximately what current across the heart is going to make my heart have involuntary contractions? Somewhere around 70 milliamps. So we have different safety levels here. If it's below about 10 milliamps, it's perfectly safe. It's just a nuisance. So you can have an electric fence, as Caitlin spoke about. You guys all missed her talk. I thought it was great. You can have an electric fence, and as long as you have the voltage such that when a human touches it, the current that's going through them to the ground is less than 10 milliamps, it's going to be safe. Just a nuisance. Now, of course, if the person is barefoot and the ground is wet, they're going to have less resistance because the human body's resistance is through the skin. And if you make that skin wet, it has lower resistance. And you have wet feet on damp soil, it's going to be much lower resistance than if you had dry feet and shoes. So you have to be a little careful with those things. Car battery. Is it safe for you to grab the two terminals with your hands? Perfectly safe. In fact, most people do it all the time without realizing it. When you're doing something like taking the positive terminal off of the battery, if the negative terminal is connected, you lean against the car, and you touch the positive terminal, the car is connected to the negative terminal, you just complete the circuit. But you don't go, ha, and sizzle, because the car battery is putting out between 12 and 14 volts, and taking into account the resistance of your skin, the current is too small for you to feel. So how can Rambo be tortured with a car battery? Yeah. You flay his skin. Get through that skin. The resistance inside is virtually 0. you get through that skin, and then you connect your electricity to that. So they douse them with some water, make sure you have some good contact in there through the skin where it's been cut, and then you can do your torture with the car battery. But you know what we don't do in physics class? We don't torture people. I know you don't all agree with that, but we don't. Okay, so safety, you get up above 1 amp, and it's actually safer than being in the 100 milliamp range because it'll just stop your heart completely. That's what we want to do when we use a defibrillator. We want to stop that sucker's heart. Why do we want to stop people's hearts? We hope that they restart all on their own just right. And if they don't, well, they weren't going to live anyway. Right? So you don't shock somebody who is in a rhythm where they're not going to die, because then you just have a potential of killing them and not saving them. And so, there's also, there's protocols you follow. But the whole goal with the defibrillator is to stop the heart in hopes that it restarts correctly. EKG and EEG, you'll see, you got a question?
What's the threshold to where it'll start causing tissue damage?
Start causing tissue damage, I don't know a number for it. It's pretty low. So, when you are, when you're using like a defibrillator, you start with the lowest level that might stop the heart because you're going to do the least amount of tissue damage, and then you work your way up. Yes, and we talked about other safety things like make sure you remove clothing. You want bare skin because you don't want to start a fire on the person's chest. That's considered bad form. Okay. Electrocardiogram and electroencephalograms. Those are measuring electrical activity in our bodies. Our brains are running on electricity. And so we can measure voltage fluctuations on the skin that tell us about the activity going on in the brain. Likewise, our hearts are just muscles, and the muscles, as we talked about earlier, you make them contract by putting voltages across them. And so you put probes across the chest, different places, and you measure the voltage differences that are making the muscles contract, and so you can determine what's going on with the muscles by looking at those voltages. So that's what the point of those two things are. And of course, you also want to make good contact, and so they usually do things like shave. So if you're having, an EKG, they'll shave the parts of your chest, making you look very manly. And for the electroencephalogram, instead of shaving, they just kind of burrow into your skin with the little probe. It's really uncomfortable. Okay, this is where we had Kirchhoffs laws. Interesting thing, the word EMF, electromotive force, old theory that said that a battery is it's putting a force on charge. Current theory says, well, no, the battery's not putting a force on the charge. It's just giving us an energy difference through a chemical reaction. So, but we still use that EMF as the voltage that can be produced by a chemical cell. Terminal voltage is not going to equal that if the battery is in use, because the battery is using a chemical reaction, and chemical reactions, of course, have rates. And if you start using the battery, then your chemical reaction has to start operating to replace, to move the charge. The chemical reaction starts. But the chemical reaction isn't instantaneous, so the voltage drops as you use the battery. Not drops over time, but drops when you use it. And so we treat that drop in voltage due to the chemical reaction like there's an internal resistance. So we take a real battery and we model it as a little internal resistance with an ideal battery. So the ideal battery is the terminal voltage if it's not used. And then we have the internal resistance. So when you use the battery, the voltage is going to drop. If that internal resistance is small, you have a good battery. As the battery gets old and worn out, the chemical reaction doesn't work as efficiently, as quickly, and that manifests as a larger internal resistance, which means when you put it under load, the voltage drops quite a bit more with a poor battery than with a new, fresh battery. Okay, Kirchhoffs voltage law and current law I already explained. you probably are going to have a circuit problem on this exam as well. So how do you solve circuit problems? Make sure you identify your essential nodes. Essential nodes are places where 3 or more wires meet. Identify your currents. Identify your loops. And by your loops, I just say go with the meshes. The meshes are all the smallest loops possible. And then you apply Kirchhoffs voltage law on each mesh. And apply Kirchhoffs current law on all but one of the essential nodes. Why all but one and not all of them? Because the last one will be redundant. It will be a linear combination of the others. And so it's not new information. The same reason why just on all the meshes and not every possible loop, because you can only have as many unique equations as you have meshes. General theory for math, you have to have as many independent linear equations as you have unknowns to solve. And so doing that method, you should have the number of currents is equal to the number of unknown currents is equal to the number of equations you have. And then you solve your system of independent equations. And you might remember I told you the easy way to solve those linear independent equations is with the matrix method. So you'd probably want to brush up on that. Of course, if you're taking any other class that has you solving problems with multiple equations, it's the easy way. Voltmeters are measuring the voltage difference between 2 points. Because you're measuring the difference, you always connect those in parallel. If you're using an ammeter, you're measuring how much is going through. You have to do that in series. So in measuring current, you put your meter in series to measure how many amps are flowing through. Of course, for your meter to not make a big difference, it needs to have a small resistance then. So ammeters have very small resistance, which means that if you connect an ammeter wrong, you will destroy the meter because it has very low resistance. The voltmeter being connected in parallel, for it to not affect the circuit, needs to have very large resistance, which means the voltmeters you can be pretty random with. You don't really have to worry about damaging the meter because it has a really big resistor. You're not going to have much current go through it no matter what you do. Transient circuits is, I actually talked about that already with the capacitor, so I don't need to bring it up again here. And we got 6 minutes. I can go on. Magnetism. Our second test was on magnetism. And so magnetism, it turns out, is just another aspect of electrostatic force. Magnetism is a relativistic result for electrostatic force. So if you're a crazy masochist, you can completely ignore magnetism and use relativity and electrostatics to solve your problems. That's really, really hard. So we don't do that. So magnetic fields come in 2 types, north poles, south poles. North means north-seeking. So if we have a little magnet and it's free to rotate, it will rotate so the north-seeking pole points toward the Earth's north pole. But then we have that little inconvenience that just like with electric charge, opposites attract. So if the north-seeking pole is pointing toward the North Pole and it's seeking an opposite magnetic pole, then what magnetic pole is the north-seeking pole actually looking for? South. So the Earth's north geographic pole is the south magnetic pole because they use the north geographic pole to name the North Pole of a magnet. So it's an interesting little idiosyncrasy about the naming convention. As I said earlier, the 2 poles always come together. You never have a monopole. In theory, monopoles could exist. There's no reason they shouldn't, but they are not known to exist. And the energy to create one, okay, so here's the reason they shouldn't. Theoretically, the energy to create a magnetic monopole is enormous, so that they could have only been created at the very earliest moments of the Big Bang, if they were ever created. And according to Guth's book, a maximum of 7 in the universe. So we're feeling pretty confident in saying we're never going to find one, even if one does exist. Magnetic fields, just like electric fields, we use magnetic fields to help us solve problems. And in fact, we never once calculated the force between two magnets. It can be done. We did not. So what did we do? We calculated the force on charges due to magnets. So the magnetic field lines, we have the rules. Magnetic field lines come out of north, go into south, form loops. So if you have a bar magnet, if here's the north and here's the south, then your magnetic field lines are going to go like that. And if I bring another magnet in the region and I put that magnet here, it's going to have a torque to orient it so that the magnetic field lines will come out of the north and go into the south. Now, we also didn't do any specific equations on that torque, but we did do the force on a charge moving in a magnetic field. And that is not an X, it's a cross. For a cross product, multiplying the perpendicular parts of the velocity in the magnetic field. So if the velocity and magnetic field are parallel, how much perpendicular parts do we get? None. Hence we get 0 for that cross product if the velocity is parallel to the magnetic field. If it's partially parallel and partially perpendicular, we have to just take the perpendicular component. Remember your right-hand rule. I saw Jonathan slyly bringing out the old right hand here because anytime you use this equation for the direction, you need the right-hand rule. So for the right-hand rule application, the first item in the two cross things is the direction of your index finger if it's just going straight out of your hand. The second one is your middle finger if it's bent. So like this, not hyperextended backward, but bent forward. And then the answer is the thumb. Now keep in mind, if Q is a negative charge, it'll reverse the direction. Right? So you have to pay attention. For negative charges, it's the opposite direction because you put a minus sign. So it'd be minus the direction of the thumb. So the right-hand rule gives us the direction of the force. And then for the magnitude, the force of magnitude is going to be QVB times sine of the angle between the velocity and the magnetic field. So you simply calculate the magnitude and the direction separately. And then you combine them and you have the vector for the force.